In this video, we're going to look at some other uses of SD besides just demonstrating entailments and theorems, which is what we've done so far. So this is what we've done. We've shown that sets entail sentences. So remember that this locution here, this means that the set gamma, whoops, you're not supposed to see that yet. The set gamma entails the sentence P. And we've also shown that sentences are theorems. And this, just the single turnstile and then a sentence, means that the sentence P is derivable from no primary assumptions, so derivable from the empty set. So it's a theorem. Now, the notion of validity in SD is just a very simple extension of entailment. An argument is valid in SD if and only if the set of the premises entails the conclusion. So here would be the premises of the argument, this would be the conclusion, and this argument is valid in SD if and only if the set of the premises entails the conclusion. So the way that you would demonstrate this then is you just take the premises, those become the primary assumptions of the derivation, and then you would derive the conclusion. That's how you would show that the argument is valid. Two sentences are equivalent in SD if and only if they're derivable from each other. Right? If Q is derivable from the set containing P and P is derivable from the set containing Q. So to show that two sentences are equivalent, what you need are two subderivations. You have one that assumes P and ends with Q, and then one that assumes Q and ends with P. And technically, they don't need to end with the sentence, right? What you technically need is the subderivation starts by assuming P, and then it contains Q somewhere, similarly with the other one. But I mean, you don't need to actually continue the subderivation if you started with P, you don't need to continue it once you get to Q. So you probably want to stop there. This is basically the same as proving this, right? Proving that P if and only if Q is a theorem. The only difference is that if you're just proving the two sentences are equivalent in SD, you don't take the final step where you apply biconditional introduction and derive this. You just have the two subderivations and then you leave it at that. And then sort of obviously, right, two sentences are equivalent in SD if and only if they're biconditional is a theorem. So we'll look at an example of proving that two sentences are equivalent. Okay, so we're going to show that these two sentences here, not A or B, and if A then B, are equivalent in SD. And so to do this, I've already set up two subderivations, one starting with one sentence leading to the other, and then the other one going in the other direction. And the tops of these just get labeled assumption because these are primary assumptions. They're not assumptions for any particular inference rule. So we'll start with this one here, this first one. So the goal sentence here is a conditional. So we're going to prove this using conditional introduction. So we will need a new subderivation that starts with A. That is our assumption for conditional introduction. And it will end with B. And now, if you look at this, all we have here is a sentence letter at the top of this. Down here, we just have a sentence letter. So I mean, this, right, we don't have a great deal of stuff to work with here, particularly at the bottom here, right, that goal sentence, there's not going to be much there. Our best bet is going to be to work top down with this disjunction here and use disjunction elimination. So we'll set up to make two new subderivations. One is going to start with not A, and another one is going to start with B, and we're going to try to derive B in both of these. And these are assumptions for disjunction elimination. This one down here is going to be very short. the one that starts with B, because we can just get it by reiteration from this assumption. As for this one up here, what you can see is we've got the assumption not A here, and we've got the assumption A here, so we can get whatever we want using the principle of contradiction. So, or sorry, principle of explosion. So we will assume B for negation, or sorry, no, we're assuming not B for negation elimination. We then reiterate not A from line 3 and A from line 2 into that. And then we've got B. Yeah, and that's the basic shell of this. The last thing that we'll need to do is just fill in the scope lines and the line numbers, which I'll do later on. Let's move on to this one here. So here we've got a conditional here at the top. Down here we've got a disjunction. Well, I mean, a conditional by itself at the top, we don't really have anything to work with, right? We could use conditional elimination if we had the antecedent, but we don't. So by itself, there's not much there. As for this disjunction at the bottom, so we could get this if we could prove either of the disjuncts. But if you go and you just plug in the truth table, so here we've got a truth table to determine whether if A then B entails not A. And I'm using the corresponding material conditional for it to make it a little easier. What you can see is it doesn't entail not A. So we're not going to be able to derive that disjunct. If you run it for B, it doesn't entail B either. So we're not going to be able to get that disjunct. So neither of those are going to work. However, if we were to assume the negation of this, if you run a truth table for that, for if A then B, and then the negation of not A or B, what you see is that they're inconsistent. So we know that we could take this, start up a new subderivation here for negation elimination. And we've got inconsistent assumptions here. We know that they're inconsistent assumptions because we ran the truth table and we've seen that this is an inconsistent set. It's truth functionally inconsistent, which means it's also inconsistent in SD. So we know that we can get a contradiction out of this. We can't immediately see how to do it, but in a case like this, typically what you need to do is need to just find a good way of making an assumption and then just roll out the contradiction. So what we'll do is let's roll out the contradiction here by assuming not A. We'll assume that for negation elimination again. And remember, doing this isn't a blind assumption because we already know that these are inconsistent. So we know we're going to be able to get a contradiction out of them somehow. Okay, so we've assumed not A. Then from not A, we can actually get this by or introduction. So that's 3 or introduction. Then we reiterate this. That's 2R. Now we've got a contradiction in this subderivation that allows us to infer A. So we've established that not A can't possibly be true because it leads to this contradiction. So you've established A. This is lines 3 to 5, negation elimination. Now we have A and we have if A then B, and conditional elimination then will get us B. Just copy that. This is lines 1 and 6, conditional elimination. From B and disjunction introduction again, we can get this. That is 7 disjunction introduction. And then we reiterate this again to R, and we've got a contradiction here in this subderivation. And yeah, and then we will have demonstrated this. This is going to be line 10, and we've shown, whoops, shown this in lines 1 to 9, negation, elimination. And so between these two subderivations, then we've established that these two sentences are equivalent.